My name is Adrian, and I'm here to talk about Gyroflow and implementing the advanced stabilization, video stabilization app in Rust. So let's see what exactly is Gyroflow. Gyroflow is a video stabilization app which takes the video as well as the gyro data that's recorded at the same time as the video to basically figure out the camera orientation in space during the recording of the video and use that to counteract the movement and to stabilize the footage. And this is as precise stabilization as you can get versus doing some image analysis. And this is what most modern cameras record internally. So you have the data mostly stored in the video files. So we just need to use that and counteract the motion and make the stabilization of the video. So it has a nice cool features. It's a modern and fast user interface. It's cross-platform. It's work on Windows, Linux, macOS, Android, iOS even. It supports a lot of different gyro sources and cameras. It has a rolling shutter correction, which is pretty important for stabilizing. And it's, of course, free and open source, and it's available on GitHub. So at this point, let's quickly go through, jump to the demo, which I will show you just in real time how it works. So this is the main user interface, and we can just go ahead and load some video. I have some prepared here. And basically, we can just hit play, and the video is already stabilized. I'm pretty sure that on the stream, it's terrible. It's just very, very slow, but you will have to trust me that it plays back in real time. There is no delays, no jitter, everything is smooth. And this really kills my demo a bit because I can toggle between stabilized and unstabilized, but if it's so stuttery, you can't see a difference. So I'm afraid that you will just have to trust me, or I can just show you the laptop for the people here. You can see it's playing back in real time. I'm not faking it here. So yeah, and this is it just works. You just load the video, and the gyro data is read from the video. It shows it here on the chart, and you can just and it applies it, and you can zoom out to see the effect of on the video, how it stabilizes it. So this is the easy file because the gyro data here in this file is actually already synchronized with the video frames. So we can just use that to stabilize. However, most of the cases, the gyro data is a bit off. It has some offset. So we need to figure out, again, this won't be visible on the demo, but sometimes the gyro data is applied for the wrong frames. So we need a way to offset the gyro to match with the actual video frames. And this is done by using optical flow to analyze the video, figure out the visual camera position, and then try to figure out where's that point in the real gyro data from the recorded device. So as you saw, probably that was I just clicked the auto sync here, and it figures out the offset by analyzing the footage, and it shows the tracked features on the screen as a green dots. So yeah, it just figures that out to figure out the offset and how to use the correct orientation to stabilize this frame of video. So we have a lot of options here. Everything is working in real time. You have all those synchronization, stabilizations, a lot of different customization settings. Everything is very smooth. Everything plays back in real time. And there's just a lot of options. It's very flexible. You can even use external data source. So you can have the gyro data recorded completely separately from the video, like with a different device, and then load it to any video, even from your phone. And it will also work. You have all this flexibility to set the offsets and everything. And after we have that, of course, everything is fast and smooth. So as well is the export. So rendering the file is just as fast. As you can see, it just goes on this laptop like butter. So yeah, this is how it works. Everything is implemented in Rust. Maybe there's no point of showing different videos because it's stuttery. So let's get back to the presentation. All right, so why even start this project? Why even create something like that? It's obviously a complex and huge application, but I needed to start it. I actually wrote it from scratch, and I need a reason to do that. So basically, I'm a hobbyist videographer. I record videos, I travel a lot, and I edit those videos later. So, and I care a lot about the video quality. I always get the latest cameras, all this fancy equipment. But when you have high quality camera and record shaky footage, that's not going to look great. So we need a way to stabilize it. And there are some current solutions that work the same way to use the gyro data. However, there was a lot of limitations with a lot of them, and there wasn't really one open source project that I can just contribute to expand the functionality. So there are just the current solutions. We won't go too much into details there because we are quite time limited. But basically, the industry standard is the Really Steady, which has amazing stabilization, but it's for GoPros only. No other cameras will work with that. And it also degrades the quality to just H.264 8-bit export only. It's commercial, there's no open source, you can't expand it, you just have what you do have. There are some vendor-specific, like from Sony Insta360 software, also some limitations, also proprietary only for those cameras. There are some other different solutions. Oh, sorry. And there were two open source projects that I could maybe use. There's a virtual gimbal, which was mainly Handler project, and the software wasn't that great. And there was Gyroflow. Gyroflow was not actually my idea. It was invented by a guy named Elvin Chen. And he written it mostly for the FPV community. FPV, like in drones, when you have the goggles and you fly the drones, record the videos. And it was written in Python. It had the stabilization that I'm talking about. It worked in a similar way. However, it also had a lot of limitations that I wasn't happy with. It was also limiting the video to 8-bit only. It was quite slow. There was no real-time playback. You couldn't see, like, in real time what the stabilization parameters do. It also had not a great and easy-to-use user interface. It was just more like proof of concept, proof of the stabilization, more like complete application ready to use. However, it was open source. So we had the stabilization code and the idea, and I could build on that. However, I needed to implement some advanced features, and being this program written in Python, it's just something you just can't do that much with Python on the lower level. So if you want better performance or some low level like GPU processing, it's really hard to use in Python. So I made the choice to use the stabilization, like the idea of Gyroflow, but rewrite everything from scratch in Rust. So that was a great starting point. And I had to, if I'm starting a new project, I had to set some goals. And most important for me was the real-time preview. We needed to have real-time playback and the stabilization in real-time in the user interface in order to see what we're working with. Because if we change some parameters, we need to see how it affects the video. Another most important thing for me is the ability to maintain maximal possible video quality, because there is no point of buying fancy high-end camera and just losing half of the information during the stabilization process. So I also aspired to be able to use that software for bigger cinema cameras for big studios. So if the software would enable that possibility, that would be great. Also, it should be easy to use, but flexible. So just drag and drop, but have all the sliders to adjust whatever you need. It should be cross-platform, Windows, Linux, macOS, ideally mobile, but that wasn't so very priority, but it was in the end possible. Also, it should use GPU processing and rendering for everything in order to be fast. It should support all gyro sources because, like, for example, GoPro records in different formats, Sony records in different formats, Insta360 records in different formats, so we need to support them all. There's just no compromise. It has to just support all. Also, I wanted it to be open source, so everyone like me can contribute. So if anyone like I was before starting that wants to add some feature, they can just go on GitHub, fork the code, add some feature, and just contribute. Also, if it was possible to also structure the code in a way that can be modular enough that the core stabilization engine can be put inside a plugin that you can implement in video editor, like Adobe Premiere or DaVinci Resolve or Adobe After Effects, that would be ideal. If you can just drag the plugin into a video editor and have the stabilization right there and then without going through an external application. So I set all those goals. It was quite ambitious. And at this point, I can say that all those goals are reached. Everyone you can see here is actually in the final application, and it works like that. So I'm pretty proud of that. And OK, so we set the goals. We needed to choose the language. Of course, I chose Rust, mostly because if we wanted to have all the sliders and see real-time what is happening, we need to have a multi-threading. We need to use all the computer power and resources to make all those computations. And thankfully in Rust, of course, it's very easy, very safe, and there is just no headaches with synchronizing and stuff like that. Obviously, this will gonna be a big application, so I wanted to be modern and future-proof, so it can be improved later, and so it won't get obsolete so fast. So Rust was great for that. Also, it was low level enough to provide maximal performance. And also, cargo and build scripts are nice additions to maintain all these dependencies and all this like build scripts to the building all the application. Also, I have to note that I'm not a Rust developer on my day-to-day basis. I'm mostly a C++ developer, and I wanted to just learn Rust and improve my skills and challenge myself to do something like more advanced. OK, we have all our goals. We have chosen the language. Now we need to start somewhere. And basically, we need to start with I like to start with hardest thing first, and then go all the way up down from here. So I figured out that we need to start with video player, because if we don't have a real-time playback of playing video without anything, then adding any stabilization won't make that faster. So we need the simplest video player that can show a window, display the video there, and play that back in real time. So for the window, I need to pick a UI framework. And I chose QML from the Qt library, or Qt, whatever you pronounce that, because it's cross-platform. It's much flexible. It's clean implementation, so it's very easy to write the user interface. And it's also light and fast engine. So there's no like full Chromium WebView thing going on. It weighs 200 megabytes. No, it's just very light, very specific to user interfaces, and it's great. So now that we have a window and user interface, we need to draw a video there. So, one more thing. We need to, but Qt is C++ library, so we need a way to use that in Rust. Thankfully, there is QMetaObject.rs, great, which handles that for us. And it's just a bridge between the Qt APIs and the Rust, so you can have structs in Rust and interact with them from the QML language. And everything is so easy, and the macros there make that so easy that you can see here just Rust code interacting with user interface, and all that you have here is just needed to create a window and interact with Rust code. So that was great. OK, so we have window. We have a way to write that in Rust. Now we need a video. So for that, there thankfully was something like Multimedia Development Kit, MDK, which actually is exactly what I needed. It takes a video file, and it hides away all those decoding, all those graphics APIs differences on all platforms. It's cross-platform, and it only cares about input file and the driving surface. So you can just provide any texture you want from the OpenGL, Metal, DirectX, Vulkan, on any other graphics API, and it will just draw that video without using any CPU memory or copies or anything like that. So it was just a perfect choice without wasting any resources, maximal possible performance, and it actually had examples for Qt and QML. So that was a great starting point. And huge thanks to the author. If anyone here ever worked with OpenGL or graphics APIs, especially cross-platform, when you have all these dependencies, that's a huge pain in the ass. So having that handled for ourselves was a very great benefit. All right, but we have the window, we have video, but so far CUDA is C++, MDK is C++, but we wanted to write Rust. What's up? So unfortunately, we need a way to hide away those differences, to use that dependencies in C++, but everything else should be done in Rust. So this is where Rust CPP crate comes in, when you can just inline the C++ code inside your Rust file, and we will just take care of all this variable passing and returning values, and it's just very easy to interchange those two languages. So I actually created a separate crate for Rust that contains all this glue code between the MDK, CUDA, and QML that it only has this specific role. It just exposes the QML component and allows you to load file and have a Rust API. So actually, in Gyroflow, is using that crate, and in Gyroflow doesn't use any C++ specific code for that. It's just hidden away in a separate crate. It's also easier to maintain, so that's why I did it that way. Oh wait, okay. So we have a window. We can draw the pixels. We have the Rust code. Now we need to figure out how to change those pixels, because we need to stabilize the video. So we need to move the pixels around, and we need to make sure that it's fast, because if we just add the stabilization and we won't be able to show that in real time on screen, we are just losing one of the goals. So thankfully, that was possible by lower level CUDA APIs to basically download the texture from the graphics memory, from the render scene, and have the pixel buffer in just normal memory. Then we can alter that pixel buffer and upload it back to the user interface. And after we have that, we can change pixels in placeback in real time. That's it. We're done. Everything else is just easy, and yeah, we can just add some user interface and it will be working. So that was the first prototype. It was actually created, it's very stuttery, but you have to believe me, it's working in real time. It was created in about 2 weeks, and it had exactly that window, stabilized footage, and the user interface in QML. So once I had that, I was pretty confident that I can continue and add features, and it will be working as I intended. So in order to stabilize the footage, we need to process the pixels. And when you have like 4K or even 8K video frame, that's a lot of pixels. So CPU is just not going to make it. We need GPU processing. And since our app is cross-platform, we also need the GPU processing to work everywhere. And ideally, I didn't want to write any platform-specific code, because that's, of course, a burden to maintain later. Thankfully, OpenGL is of the most obvious choice. It works everywhere. It is well supported on every device. And I implemented the pixels processing using OpenGL. It worked great. However, OpenGL is just basically external dependency, so that's not ideal for our case. Also, it was sometimes failing to initialize. So yeah, I wanted to add some other way, some other fallback. WGPU project is a great way to do that. It's similar to OpenGL. It allows you to run compute shaders and graphic shaders, and it's pure Rust. It hides away all those graphic APIs differences, and it allows you to have one single API to call all this GPU processing. So I actually ended up implementing both in OpenGL and in WGPU, the shaders for the processing. And we have two different fallbacks of GPU fallbacks for the processing. And also we have, of course, the CPU-only processing when you use that app on computer without any GPU. So that also works. That's using, of course, implemented in Rust using Rayon. So it's also using all the CPU cores. So far we're working on pixels buffer in the memory, in the user memory, because we downloaded that from the texture. We have the pixels buffer in the memory, and we pass that to OpenGL or WGPU. However, I figured it should also be possible to do zero copy and the stabilization, because we have the video decoder on the GPU. We have the uploading to the graphic interface also in the GPU. So copying that to host memory only to upload to OpenGL and then back and forth, that's a bit of waste of computational power. However, we also need that way. We also need this computing path if you want to implement the video editor plugins later, because they give you just pixels buffer as a host memory as a memory, so you need to upload that ourselves. But for the main user interface, it was also possible to implement zero copy preview, which actually doesn't use CPU at all. So everything from the decoding, to the stabilization, to the uploading, to the actually not uploading, to the displaying on the user interface is done entirely on the GPU. And I have the example here. Of course, it's not smooth on your screen, but you can see that the CPU usage is basically to 0. And that's stabilizing full 4K frame of video in real time. Okay, so we had that. That's great working. Everything is fine. Like I showed you before, sometimes the gyro is not perfectly in sync with the video, so we need a way to offset that, to basically figure out which gyro sample is for exactly this video frame. And we employ the optical flow to do that. In the Gyroflow Python version, that was implemented using OpenCV because it's just the easiest thing to do. And here, I also implemented that using OpenCV, the same functions. However, I don't really like adding all those dependencies because that's a huge pain maintaining later. And I figured out ideally it should also have a way to be implemented in pure Rust without ever needing the OpenCV dependency, because that's huge. Thankfully, there's a Rust CV project which has the right algorithm for optical flow, and I was able to also implement that to ditching the need to ever use OpenCV. However, OpenCV is still a bit faster because the algorithm from Rust CV is a bit advanced and not GPU accelerated. So I just have two options for user to pick. But the OpenCV dependency in the code itself, in the Rust, is just optional. So there is no need to employ the full OpenCV. If you want to compile for some exotic target, you can just use pure Rust and it will also work. Also, if we figure out the optical flow and then visual camera position, visual camera orientation, we need a way to figure out which offset to use to match that with the gyro data. And that's basically taking all those possible offsets, like from 0 to 1,000, and then figure out the distance between the visual camera and the gyro camera orientation. And this is a perfect job for multi-threading, and Ryan comes here very, very well. And I don't intend to explain all this code, but this is literally all it takes to figure out the offset using full all the cores of your computer. It's very clean, no explicit synchronization. Everything is just very, very easy and readable in the source code. So that was a great example to use multi-threading in Rust. All right, so another thing that is very important for stabilization is rolling shutter correction. That was not implemented in Python version. That was one of the drawbacks of the previous implementation. And it's really essential for some cameras, because when the camera is capturing the video, it's not capturing all of the pixels at once, but it's actually going from top row to the bottom row. So when you move the camera quickly, the top row is captured at a different time than all the different rows. So it creates this wobbly effect when you are on the straight lines, so because they are captured at different times. So if we stabilize the footage with that, we will still have wobbly video, because that was just an artifact of the camera sensor. So we need a way to counteract that, to figure out how to straighten those lines first and then apply the stabilization. And the idea is actually amazingly simple, and implementation is even simpler. It's just a few lines of code, but there is just not too much information online or descriptions or open source examples how to do that. So it will not be visible here, but maybe if you look at the straight line of the window, you can see that it's warping. And here, after the rolling shutter correction, it just remains straight after the stabilization. It's really a shame to not see that in real time, but yeah, we just have to live with that. It's of course working in real time. Even this rolling shutter correction, everything is still in real time. Yeah, sure. I can see. I can show you here. Just a second. and then the corrected version. Yeah, and all of that is still running in full real time with no additional delay. And the idea is very simple. If you have the first row of the video taken at a different time, recorded at a different time, then we just have to use different quaternion, different gyro sample from a different time. So it's actually using different data from the gyroscope for every line of the video. So, and it's just going from the full resolution top to bottom and uses like 4,000 different data sources for one frame. So it's really simple to implement once you understand how to do that, how to counteract that, and it turned out to be working very well. So yeah, now we have all the stability, and the stabilization itself is really not that big of a deal. It's very simple. If you have the rotation from the gyro, you just apply that to the pixel and move this according to this rotation matrix. So the stabilization itself is pretty simple too. So we have all of that. Everything is working great. Now we need to render things because there's no point of just seeing that in the user interface. We want to this video rendered. The obvious choice here is use FFmpeg to support all those different input and output formats. But we also want to employ the hardware acceleration here, both for decoding of the video and encoding of the video. And it turns out that while it's easy on the CLI application of FFmpeg, using the C APIs directly is very complicated. There is barely any documentation or examples, and it's really a lot of functions to call, a lot of different devices have some dependencies. It's a nightmare. I don't wish that to anyone. However, I needed to implement that, so I had to figure out that some way. And reading the source code of FFmpeg CLI program was the only way to figure out what needs to be done. And a great trick here is that when you have the GitHub project open, like for example the FFmpeg the project on GitHub, you can just press dot on your keyboard and it will take you to github.dev, which is actually the Visual Studio Code fully in your browser with that file open. And you have all this go-to definition, find in files, and all those features of Visual Studio Code without installing anything or forking or cloning anything. So that was really, I use that a lot when going to the code to understand what needs to be happen. And yeah, that's a nice trick to know. Okay, we have hardware acceleration. We can decode the video. We have the pixels data, and we can put it into an encoder and produce the frame. Now, the video actually in the file, most of the formats is not stored like images. It's not using RGB. It's not like it's a single plane with RGB values and repeated throughout the video, throughout the full frame. It's actually stored using YUV format, which is using full resolution grayscale image, like the brightness of the video, and then it uses half resolution color, two separate half resolution color images to overlay them on top of the grayscale image to produce full RGB color. And it's done that way to save space, basically, because human eye is not as sensitive to color changes as it is to brightness changes. So if we can lose the half of the information in the color, we can still perceive the full image as a very high quality one, because we just can't see those little differences in the color itself. We only look at the details in the sharpness of the brightness of the video. And this is how the data is stored inside the MP4 file or any video file, basically. But all those different processing functions or decoders and encoders, when you have the decoder, it will automatically scale those color planes up, produce the RGB image from that, so doing some calculations with the pixels, and then you can process the RGB, and then it repeats to scale them down, separate the brightness, and write to the file. I figured that's a waste of computational power. We don't actually need the RGB image to process it. We don't care what it looks like. We just want to move this pixel to this other position. So we don't care if it's RGB or anything else. So I figured, let's just take those planes directly, like the grayscale plane, the full resolution grayscale plane, and just apply the stabilization to that. And repeat that for the color planes, but actually at the half resolution. So we don't need to scale them up, then process, then scale it down. We just take those planes as a separate videos, basically, and stabilize everyone separately and write that directly to the output file. And this turned out to be working very well. We gained a lot of performance by not scaling up and down and figure out RGB pixels because that's not needed. And this is actually implemented in Gyroflow. So it also allowed us to maintain full input quality because we are not scaling up and down things. We're just moving the pixels as they are in the file. So that was one of the better ideas to how to make this the whole application like the next level to comparing to all the competition. Okay, so once we did that, okay, we have everything is rendered, everything is working. That's great. One of the goals was actually to have the code structured in such a way that we can just use the core module, core stabilization module, and create a plugin for the video editor. So the point is that we should have pure Rust code that will take only input parameters or input file and input pixels as a raw pixels, and then output the stabilized pixels. We don't need user interface for that. We don't need any OpenCV. We don't need FFmpeg. We don't need Qt. We don't need any external dependencies. You can just do that in pure Rust. And I actually implemented the core module that does that as a separate crate that the user interface uses. So it's very modular and it can be used exactly for that purpose. So actually, after releasing the code, the first plugin that you can use in DaVinci Resolve, for example, was implemented just after 3 days of releasing the code in just 300 lines of code. So it just took the pixels and output the final pixels, and this works very well. So yeah, I guess next goal was completed. Everything was working as intended. It was great. It was actually implemented by Ilya Epifyanov, which huge thanks for him. He did a great job to implement that. All right. We have some details here how to ensure max performance, but I think we're running a bit out of time, so I'll just go quickly through them. Basically, we don't want to repeat if you have one pixel for the full frame, we just need all the calculations for this particular pixel done in a single step to not repeat all those different layers of computations, because when you have like 10,000 frames or 4K frames to process, that tends to slow down things a bit. So everything should be as simple as possible in a single step. Then whatever is the same for the whole frame of the video should be calculated in Rust beforehand. And then the kernel that's actually run on the GPU for the pixel should not repeat those calculations. That's just a waste of computational power. Also avoid copies at all costs possible, because 8K frames with some advanced pixel format, they can occupy a lot of space, so there's no point of copying that for the most part. And also, we want to ensure that when you change the slider, you want to see the result in real time as soon as possible. So we can introduce some delay, some debouncing, but that wasn't an ideal solution for me. I ended up using thread pool to queue all those calculations that you do while dragging, and then interrupting every not relevant one early and only leaving the latest one. So you can actually don't feel any delay while doing that, while using all those computational power that you want. All right, there are some unexpected issues and that I encountered. There was a lot of figuring out what went wrong, especially for the quality degradation, because there was actually a quality degradation after exporting. And remember, I structured everything away to basically prevent that, to use maximal possible input quality, just take the input pixel, move it around, don't mess with it any more than it needs to be. Actually, after I didn't notice that, but after releasing, some user just pointed out that the quality is degraded a bit. I couldn't even believe him at first, because there's just no way in the code to the quality to be degraded, because everything is so simple. And actually it was, and it wasn't my fault, so that's great. It was actually done by FFmpeg, where there's basically a different representations of the YUV format. There's different pixels formats. Some are stored in, the idea is the same, but the pixels in memory are stored in a different order or some different formats. So we need a way like this codec only supports this format, this codec only supports this format. If you want to transcode from one to the other, we need a way to convert that. But in theory, that should just move the byte values around in memory without using any scaling or interpolation, because it wasn't scaling up or down the video. It turns out that the FFmpeg function that uses to convert the pixel format was actually doing the scaling. And it was very surprising to me, but it actually took the interpolation function parameter, but I figured I can just use the fastest one because we are not doing any scaling. It turned out that it does scaling for some reason, probably because it supports a lot of different pixel formats and conversion between them, so they have to make some compromises, and that turned out to be the fault here. It actually made the video blurry after doing that. After I changed the interpolation function to be something higher quality, it solved that issue. So huge thanks to this user who reported that. Now we have actually tested and everything maintains the highest quality. There are also some other issues. I won't go too much into them. So that was most of the way that I implemented all of that. So let's see how it ends up today. Everything that I said here is implemented using just 10,000 lines of Rust code. 5,000 is only for the user interface, because as you saw, it's quite advanced, a lot of stuff going out there. And you have only 800 lines of C++ code, which is also including the glue code for the MDK and CUDA dependencies. So I really tried to keep all this C++ code to the minimal. 800 lines is really not that much. All right, everything that you saw here up to the first public version that had all the features that I showcased and all the goals finished, took just 4 months of work, basically me alone. And first functional version was implemented after 1 month. And it was like I started implementing from scratch using the process I described it. Then after 1 month that I had the full functional version, I took them to the creator of the Gyroflow, the Python version, and we talked about, and we said, okay, I will just re-implement that. We will use the same name, the same logo, the same process. We'll just move all the code base and user base to this new Rust version. And then he joined me, and we continue with implementing all those different advanced, more features. So currently, it was made public in February. So we have March. So only 2 months ago, basically, we have over 3,000 stars on GitHub, over 40K downloads, about 10 contributors already, and 20 user interface languages. So it's really good, I would say. Okay, I won't go too much into detail here. The most important thing that I want to showcase here is that I know that Gyroflow is actually already used for the big productions for Red Bull, BBC, National Geographic, and Disney+. Most likely also for Netflix, but that's not confirmed yet, so I didn't want to say that here. And yeah, I'm pretty happy about that. That worked great. Special thanks to all the team, of course, Elvin Chan for creating the idea of Gyroflow and the first Python version, all those contributors here, testers. I actually ended up creating two separate crates that hide away on different portions of the Gyroflow. One is to parse all those different data sources from the video files, and another one is, like I talked, to hide away the MDK and C++ glue code for the user interface. So that's basically it. That's how I implemented that.